Hello everybody, welcome back. Today we're going to be doing our first video on shear moment diagrams. And this topic is super important to the Strengths and Materials course, so I wanted to take it very slow and pretty much introduce the topic to you guys using what we learned before from internal force problems previously. So I'm going to take this problem very slow at first and explain all the details and kind of take it very slowly. Okay, so the next video is going to be a little bit faster when we're solving. So if you don't need a detailed explanation, you can skip ahead. But just for now, I'm just going to introduce the concepts. So let's look at our problem here. Draw the shear and moment diagrams for the beam. And we have this simple span here. But before we get into solving this problem, I want to explain what's happening in a shear and moment diagram a little bit before we actually hop into it, okay? So, similar to what we did before with internal force problems, we are now instead analyzing multiple sections along the beam to determine variations in shear and moment, okay? So let's take some points that we know already, right? If we look at our pin, we know that there's going to be a reaction in the y, but there's no x reaction because there's no x forces applied to the beam. So let's imagine a y reaction here. This is going to be a positive y reaction based on this distributed load and this F load applied, meaning that it's going to create a positive shear at that point based on that reaction. And we also know at a pin, there's no moment produced. So there's going to be zero moment in this diagram as well at this point. And then similar with the roller, you have a positive reaction as well, which is going to counteract the shear that's created at that section, bringing our beam back to zero at the end to keep it in equilibrium, okay? And similarly, we have no moment that is produced as a reaction at the roller, so there's going to be zero moment here in the diagram as well. And all we need to know for now is that if we take any point along this beam, let's say a point in the middle, we can determine the shear force and the moment produced at that point simply by solving for these bending moment and shear diagrams, okay? So, since we're no longer analyzing specific sections in these problems anymore, we have to take arbitrary sections using the distance x to create functions for a moment and shear along each member span, okay? So I have 3 different x values right now for 3 different sections of this beam. But how did I know what sections to pick? I picked these sections because our function will change as external forces are removed or introduced to the beam. So we have this distributed load first, and as it ends, that brings our first section to a close. Similarly, with x2, we have the constant section with no forces applied. And then for section 3, after that F is applied to the beam, we have to consider another section as well, okay? So these functions, in combination with our equilibrium equations and internal force conventions, will allow us to solve for critical values, okay? What are those? A critical value would be any point at the start or end of our sections that we solve for. So if we had a point here and a point here, we can actually interpolate between the points so that we can get the entire shear and entire moment along that section. So the function is super important to solving each section, right? Because we can plug in our x values, starting with an x that is unknown, and then plugging, let's say, x is 0, and then x is equal to a in order to get those 2 critical points to interpolate between, all right? So the function's degree is also important as well as we continue through these problems because it will indicate whether we're positive or negative in shear and moment, and it will also indicate the curvature of each graph, right? So you can see here that we have a linear function for shear, and we have a quadratic or second degree function for our moment diagram. And then as you move along, you can see we have a constant here and a linear here respectively. And this will all make a lot more sense when we actually start solving for these functions for the spans here. But we could actually make this a little bit easier on ourselves because right now I'm considering 3 different x values. But what we could do is actually just consider one x value and use that for each of these spans, right? But why can I do that? I can do that because if we solve for span 1 first, let's say, and move to span 2, why don't I just consider the x value between this section and then make the section prior a constant value? That would make our lives a lot easier because this W distribution, let's say, would no longer be decided by a variable x because we know that the span that it covers is a. It's no longer a distribution that we need to solve for based on an unknown length, right? So if we apply this knowledge to a different diagram, we can actually look at the problem like this. So now I have the diagram updated for what we just talked about. You can see that I switched to a constant x value, but our x value is going to be changing based on the span that we cover, okay? So the first span, we're going from 0 to a, so x has to be less than a, but greater than 0. Then similarly, moving to section 2, we now consider a new span of x minus a, because now a is not being represented as a section that's analyzed by a function, but rather as a constant span. And we consider that x needs to be between the values of this point and this point. So x has to be greater than a, but less than b. And b is where that new F external force is applied. So that means we need to start a new section. And then similarly for section 3, it follows a very similar concept. So now that all of that is explained, let's try and hop into this problem and see what we're dealing with when we're actually trying to solve for a shear moment diagram. All right, so similar to what we've done before with internal force problems, we know that our first step to solving any beam like this is going to be to find our reactions, okay? So we have our pin here, where we know there's going to be an AY. We have the roller here, which will be CY. And then just for fun, we're going to solve for FR as well from this distributed load, just to make our lives a little bit easier. So the first thing I want to do is just simply get FR, and that is going to be 1.5, the peak of the distributed load, multiplied by the span it covers, which is 1 meter. The meters cancel out, meaning FR is going to be 1.5 kilonewtons. Then we can go ahead and solve. Let's just take the moment at A to solve for that reaction CY, and we know that's going to be 0, and our convention looks something like this. And solving is going to be the negative 1.5 because it's creating the clockwise rotation about that point. And it's 2.5 meters away. Why 2.5? Because 2 plus half of 1 is 0.5. 2 plus 0.5. You get the idea. And then CY as well, which is 3 meters away from that point, meaning that when we solve for CY, we will be left with 1.25 kilonewtons. And then we can go ahead and take our Fy to solve for the reaction AY. And when we do that, we have AY minus the FR, which is what? 1.5, plus the reaction we just solved for, which is 1.25, meaning that AY is going to equal 0.25 kilonewtons. Now the next step to solving these types of problems is going to be to take our sections, right? So looking at our template here, and recalling what we just spoke about, we know that every time a reaction or a force externally applied ends or starts, we have to start a new section. So we're going to have one section here, and that will be section 1. And then the other side will obviously be our section 2, because this distributed load goes all the way to the end of our beam. So let's plug this in to a template like this and see what it's actually going to look like. Okay, so now we have the problem plugged into our template, and we can see that we have two separate sections based on when external forces are either removed or introduced. So for section 1, we need to first determine what x values are feasible when we have a function for this section, okay? And that will be simply 0 to 2, because the span of this section is 2 meters. And then similarly, we have 3 meters for this entire span, so that means this section is going to be only 1 meter, therefore x has to be greater than 0 and less than 1. All right, so now where is our x actually acting? What do I mean by this? Well, let's say we have an x value going from left to right for this section, because we want to start from the simplest direction. We can't start from this right side yet because we obviously have all of this undetermined section behind it. So we're going to go from left to right on this side. But that also means it's possible for us to just take a section from right to left on the opposite section, because we're starting from one end and working our way out, and we don't have to focus on any of this section when we work here, and we don't have to focus on any of this section when we work here. So that's the logic behind the direction that these x values are chosen. So now that we have this determined, we can actually go ahead and take some internal cuts. So for section 1, let's take a cut just arbitrarily there. We'll take a cut arbitrarily here for section 2, and we'll take a look at what these internal force free body diagrams are going to look like. All right, so now we have the internal cut made, and we can actually start solving for moment and shear based on the span x, which means that both the moment and shear calculations are going to be a function. So let's start with moment first since it's a little bit trickier. We'll solve for m1 equals 0. The m1 notation is just to signify that we're working in section 1. And let's get to solving. Let's see how different this is going to be with an x value. So we have the moment acting in the positive convention. So we have m1 positive. Then we have this reaction here. And we're considering the moment from this point at the end of our cut. So that means the distance from the point to the reaction is always going to be x, meaning we have negative 0.25 times the distance x. And then simply solving for moment, we are going to be left with 0.25 x, and that value is going to be in kilonewtons per meter. Pretty cool, right? So now we have a moment represented by an x function. And what is this function? There's some things we can point out quickly. We can see that it is going to be first degree, meaning that the diagram that we're going to draw for this is going to be linear. And what did we say before? We need to solve for our critical points in order to plot anything on this moment diagram. So what would be a critical point here? Critical point would be at x equals to 0. And we know that at x equals 0, when this x value is 0, moment 1 is also going to equal 0. Then we also need to consider the last point at the end, which is going to be at x equals 2 meters. And when we plug that in, we have that moment is going to equal 0.5 kilonewtons per meter. And just like I said before, we can plot these points. So let's have a point here and a point here. So we have 0 here, and we're going to have 0.5 here. And then we can interpolate a line between these 2 points, which is going to be linear, and simply have the moment diagram solved for section 1. And then similarly, we can solve for the shear force as well by taking the Fy summation equal to 0. And when we do this, we are simply left with obviously this y reaction. So we have 0.25 minus the shear force, which is going to be V1. Solving for V1, we are left with 0.25. And you notice that there's no x involved in this. So what does that mean? That means that we're going to have a constant shear diagram for section 1. So we can put a point here and a point here, and we can say 0.25 is going to be the constant shear value for this section. So let me update this drawing so we can visualize what the moment and shear diagram will look like. So now that the diagram's all filled in, you can see that the moment and shear diagrams are going to be positive because our convention assumes a certain direction where if you solve for the moment or shear and you get a positive sign for both of them based on your convention, that means on the diagram it will also be positive. So since we got positive answers for both of these, that means that our diagram will be positive. So let's move on to the second cut in section 2 and see what we're dealing with there. Okay, so now I have the second section made, and this is where things may get a little bit tricky, but I'm going to try and explain it as easily as possible for the first time we do it. All right, so you can see here that we have the cut made following our convention from previously, and we have the x from right to left between 0 to 1 is our values that we can use. And we have this FR here, but now I've changed FR to a question mark because FR was previously based on the span of 1 meter, but now we have to base it off the span x, right? So that means FR is going to equal 1.5 times x. So far, so good. Well, here's where things get a little bit trickier. Let's solve for Fy first in this span. When we do this, we have the FR and the reaction here. So FR is going to be 1.5x as we solved for previously in the negative direction, plus the 1.25 reaction from before, plus the shear that we have as well. Solving for shear, we have 1.5x minus 1.25. All right, so now we have a function for shear. When before it was constant, now we're going to have a linear function because we have x to the degree of 1, okay? So what do we need to do? We need to find our critical points, right? So what are our critical points going to be? We have our first point here, but we already know what that point is going to be because this shear is going to be the same on both sides of this section. So we know 0.25 is going to be that starting point. we can solve for this point here, which is going to be based on x equal to 0, because we are starting from right to left. So this is actually considered our 0 or our origin, let's say. So when x is equal to 0, we know that V2, or shear at section 2, is going to be equal to this value, negative 1.25 kilonewtons. So we could plot a point right here for negative 1.25, and we can interpolate a line between these 2 points. So now we have this line interpolated between the 2 points, and we can see that it goes from positive shear at the starting end and then works its way down to a negative shear. But what does this do? This introduces a new critical point, which is something we talked about previously. And that critical point is at this point here, this x value that we don't know. Why is this value critical? This value is critical because it is going to be the apex of where this moment diagram is going to be, the peak of that moment diagram, right? So we need to actually interpolate for where that x value is going to be. So how can we do that? Well, what we can do is actually set our equation for when shear is equal to 0, because we know at this point between positive and negative, this point has to be 0 shear. So when shear at section 2 is equal to 0, we are going to have this equation isolated for x to get this location, right? So what is it going to mean? We have x will be equal to bringing it negative 1.25 over, so we have 1.25 on top, divided by the 1.5 to solve for that x value. And we have x equal to 0.833 meters. So what does that mean? That means this apex, wherever it is going to be 0.833 meters from right to left to get to that point. All right. So now we can move on to solve for our moment calculations here. So how are we going to do that? We're going to do it just as we normally would. We are going to take first our summation of moment at section 2 equal to 0, considering our convention, obviously. And we have a similar problem as before. Considering this point, we have the FR creating a clockwise rotation, meaning that's going to be negative. And we solve for FR as 1.5x from previous. But now, what is this x value? Where is this distance going to be between? We have to consider half of x, so 0.5x. Why is that? Since the center of this distributed load is going to be changing based on this function x, we can't specifically say a number for what this point is going to be, but we're going to consider the function of half of x as where that centroid is going to be acting no matter where you are in that span, right? So that's why we consider half of x. Moving on, we can take the 1.25, that is going to be positive for a counterclockwise rotation, and we have the distance x from the cut to that reaction, it will always be x. And then obviously including our moment, creating clockwise rotation about that point, and solving, we have moment at 2 equal to this function here, 0.75x squared plus 1.25x. But now we have a different degree that we haven't seen before. We have a second degree function, meaning that the curvature here is going to be quadratic, right? So what do? We have to solve for our critical points once again. So what are our critical points going to be? Well, we know, as we discussed previously, either side of this section will be the same. So we know this point is going to be 0.5. And we already discussed earlier that the moment at a roller is going to be 0. So we also have another point here. So we only need to solve for what this apex is going to be. So solving for that, we need to plug in x equal to 0.833 into this equation. And when we do that, we're left with m2 equal to 0.521 kilonewtons per meter. So we have a point just about here, and let's see what this graph is going to look like. So now that we have this interpolated, we can see that we have the apex of our moment diagram at 0.521 kilonewtons per meter. And if we look at the curvature, we can see it's a quadratic function. And our peak is at that intercept between positive and negative shear. And we're going to learn in our next video the relationship between the shear and moment diagrams and how we can use the diagrams more effectively to help us solve these problems. I know this one was pretty tricky and pretty long, but I really wanted to cover the basics before we got into any solving. And I wanted us to just strictly think about, values rather than tips and tricks on how to solve these problems more efficiently, right? So I hope this video helped, and I'll see you in the next one.